The brain dump from Wednesday's lecture is here. I'm going to exclude the discussion of Kriege intermediates and just roll through what we were doing with emphasizing again what's going on with the particle on the ring, using Slinky as a model. So the first important part is that when we have motion in the XY plane now, going in a circle, kind of a hula hoop around a ring, starting at X and then heading around in a counterclockwise direction toward Y. We do this in polar coordinates shown in purple with a radius vector r that we're going to hold fixed on the hula hoop. That's why it's called a particle on a ring. And then the variable is phi. And this is a model, actually. The only thing it's a good model of is what we call internal rotations of molecules. So if there's really only one dimension in play, and there's, let's say, a hydrogen rotating around, there's a free OH group, let's say, with a hydrogen rotating in circles around the axis of a CO bond. If there's an alcohol moiety there with an OH spinning around entirely freely, then this would be a good model. So we're rotating in the XY plane. The axis of rotation is the z-axis, and that's also the direction of the angular momentum variable. So to get the direction of the variable, we do the right-hand rule. We stick our finger out along the r, the radius direction. We curl our right-hand fingers in the direction where phi is increasing, and our thumb is pointing in the direction of the vector. So that's x cross y, or r cross phi, and we get the z positive dimension. And the important thing is that if the function is going around once, if the function is cycling once as we go around in the circle, we go from 1 to I to -1 to -I, as shown here in red, and that corresponds to a rotational quantum number m sub L equal to 1. And the momentum, Jz, is h bar. So it's a unit of h bar. That's the other amazingly important thing, is that the angular momentum comes in units of h bar. The next possibility is that m equals 2, and in that case, shown in orange, we go from 1 now to I at 45 degrees to -1 to -I to 1. We get back to 1 when we get around halfway around the circle, and then we go to I to -1 to -I, and finally we come back around full circle, having gone twice through that cycle, 1I -1 -I1, 2 times around. So here m sub L is equal to 2, Jz is equal to twice h bar, so again they're units of h bar in the angular momentum, incredibly important. Another possibility is we're going in the other direction. In green, we go from 1 to I to -1 to -I, but we're going the other way around. So the j vector is pointed downward, and that's an ml in green of -1, and the angular momentum Jz is equal to -h bar. The other main thing is that we're so used to counting nodes here and zero crossings, and I've been emphasizing that. Nodes, 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 nodes. In this case, with Slinky, Slinky never crosses 0. That's the whole point. That's one of the whole values of this complex function. So instead of counting nodes, we're going to count cycles. How many times around from 1 to I to -1 to -I back to 1 does it get? So if m sub L is equal to 1, it goes one cycle around the complex plane as you go from 0 to 2 pi. That's the equivalent of one node. So the number of nodes in these Slinky functions is just equal to that quantum number, the absolute value of that quantum number, m sub L.